talk a little bit. We'll kind of continue on what we've been talking about, which here at the end, which is our alkenes and our alkynes. And once again, the functional group here for our alkenes is a carbon-carbon double bond. The functional group for our alkynes is carbon-carbon triple bond. And they are based off of obviously the alkane names. So as we talked about at the end there's a couple of different sort of things that we got to think about when we do these guys. And that is, again, the double bond or the triple bond does take the priority in terms of numbering. So again, if we had something, say, like this. Just make something up here, see how we do. All right, let's do something like this. So why don't you take a second here and try to give the proper name for this guy, and then we'll do one more. Let's do take a look. So the longest carbon chain here, remember, it does have to contain the functional group. Should be 1, 2, 3, 4, 5, and 6 going that way. Again, if you go straight across, you only got 5, but you can get 6 by going that way. That would give us the base of the name, which is based off of hexane. But here it does have a double bond, so this is going to be hexene, E-N-E, at the end of it. Any questions on that? Now, in terms of numbering, we do want to go whichever way gives, in this case, the double bond the smaller number. So going left to right, 1, 2, 3, 4, 5, and 6. Our other option obviously would be to head in the opposite direction, where that would be 1, 2, 3, 4, 5, and 6. Obviously, going in the first direction, that gives our double bond a location at carbon number 2, which is the way that we do want to number this. Question on that there? So we don't want these guys. So that would mean that this would then be 2-hexene. At this point, we do have a chlorine and we do have a methyl group that's there. And because of the way we lock the numbering in, that is the way we have to number the rest of the group. So because we're going in this direction, that means that carbon number 3 is my chloral group. And at carbon number 4, that would be my methyl group. So putting all that together in alphabetical order, 3 chloral, 4 methyl, 2-hexene. Any question on that name there? Looking at the one at the bottom there, we could go straight across. Gives us 1, 2, 3, 4, but we could also go 1, 2, 3, 4, and 5 going in that direction. And that is what we would want to do. That is more. So that again, in this case, is going to be 5, which is based off of pentane. Has a triple bond, which means this becomes pentyne, YNE. Giving our triple bond the priority, that means carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Obviously, if you go in the other direction, that triple bond is going to have a much larger number. So this would be 1 pentyne. Because we locked our numbering in this direction, that means at carbon number 2, there's a bromol group. And at carbon number 3, there is a methyl group. And that means that this would be 2 bromol, 3 methyl, pentyne, YNE. Any question on that name or any of those names? Yeah. We did put, thank you. We should have put the number. I did above, but not there. You know, it happens. There's a, there we go. That's good. All right. You are correct. We do need the number, and there it is. 1 pentyne. Thank you. It should look like that. There we go. Got it there. Just left it off when I put it together there. Other questions on that there? Okay, then let's do some names here. Back to formulas just to make sure. Let's do 3-ethyl 4-pentene. And let's do 3,3-dimethyl 1-butene. Let's see what we come up with there. You could draw the condensed formulas for each of these there. All right, let's take a look. So once again, we're going to work backwards here. So pentene, that's based off of pentane, which means we should have 5 carbons. And ENE means there's a double bond at carbon number 4, which is what the 4 means. I'm going to call this carbon number 1, which means carbon number 4 for me. 3, 4 would be here. And that is where we will put our double bond. And that takes care of pretty much this and this. That means at carbon number 3, there's an ethyl group, which is a 2-carbon group, which would go there. And now everything else again would be hydrogen. So this guy needs 2. This guy needs 1. This guy needs 1. Coming up, it needs 2 and 3. 2 and 3 again to get everybody to 4 bonds. Any questions on that one there? Now, this also illustrates a point that if you were given the structure, you would call it a different name, but that sometimes happens when you draw it from the name. You know, if you were going the opposite way, you would actually give this number 1 and kind of go that way, but sometimes happens. Coming on this one, which is butene, so that is 4 carbons. And it has a triple bond at carbon number 1, which would be here for me. That means that this is carbon number 3, which would have 2 methyl groups. That's the dimethyl, and they're both at carbon number 3. And now we're just put our hydrogens in, which would be 3 here, none there, and just 1 there, basically. Yeah. Any questions on any of those there? So again, it works the same way as, you know, doing the other one. Just kind of do with the base of skeleton, put your double bond or triple bond in, and then obviously all the other groups. Any questions on those there? Now, we talked about isomers earlier, and when we do have double bonds or alkenes, they do create what are sometimes referred to as cis or trans isomers. And these are isomers that happen because when we have a double bond, it is rigid, which means there's no free rotation. When you have a single bond, all those groups can rotate all around. That's why you could draw it up, you could draw it down. It really doesn't matter. But when you get this double bond, it pretty much locks everybody into place. And what cis means is the groups are on the same side of the double bond. And trans means that they are on opposite sides. So there are a couple of rules to decide whether or not you actually can have a cis or trans isomer. So it all really does revolve around the carbon-carbon double bond. So you want to isolate those guys. And then when you look at the carbon-carbon double bond, on one carbon, there needs to be two different groups attached. So these two guys need to be different. On the other carbon, you also need some different groups. And if that is the case, then it is possible to have a cis or trans isomer. If you look at one carbon and they have the same group, then it's not possible to have cis or trans. The other thing that you would then look for is, are there groups on opposite carbons that are the same? And in this case, the A and the A are the same, which means they're on the same side of the double bond. So this would be a cis isomer in this case, because these two guys are on the same side of the double bond. So you got to have different groups on each individual carbon. Then you need to have at least one group that's the same on opposite carbons. And if they're on the same side, it would be cis. If we had the same guy here, like this, say, this would then be trans, as they're on opposite sides of the double bond. By the way, for cis, they both could be up or they both could be down, just as long as they're on the same side of the double bond in that particular case. So when we look at these guys here, let's take a look at, say, something like something like this. So the first thing that we would want to focus in on is the carbon-carbon double bond, which is right here. And then on that double bond, you really should find two groups on each carbon. So we have this guy here, which is a group. We could even count the hydrogen as a group in this situation. We also have a hydrogen on this side, and we have this group on this side. So first off, these two groups are different. These two groups are also different. So that means we can't have a cis or trans isomer. The group that's the same on both of these guys is, you could look at this group, right? And you can look at this group, they're the same. They're on opposite sides of the double bond. Yeah, one's up, one's down. That would make this the trans isomer. Yeah, so this would be the trans isomer. You could also look at the hydrogens, which are on opposite sides as well, to tell you it is trans. I guess this would have been better drawn down this way, maybe. Like that. The better illustrated, I suppose. So when we look at something like this, let's take a look at the, flip a page here. This would now be the cis isomer here. Once again, this group and this group are on the same side of the double bond. So that would be cis. By the way, if we were to name this, What is the longest carbon chain here? Longest carbon chain is how many here? So very common when people see these things drawn as cis or trans, they only focus in here. But you could start here. That's one, maybe 1, 2, 3, 4, 5, and 6 carbons. So this is really, even though it may not look like it, this is what is called cis hexene, and we do need to give the location of that double bond, which in this case would be 1, 2, 3, no matter which way you go. So this would actually be cis 3 hexene would be the proper name for this guy. So we put sometimes cis or trans in front of the name. The other guy on the previous page would be trans 3 hexene was the previous page, which looks like this. That would be trans, and this would be cis. Question on that there. So if we had, say, this here. And if we had actually this here. All right, is cis or trans? None of them. What do we think? So then we want to focus in on what's attached. So we have this group on the left carbon and this group, so they are different, so that's good. We have this group on the right carbon and this group on the left, on the right carbon, which is different, so that's good. Now, is there a group that is the same on opposite carbons? In this case, it is the methyl group, right? And they are on the same side of the double bond, which means that this guy would actually be the cis isomer here. Any questions on that there? Coming to the guy on the bottom, we do the same thing. We want to focus in on the carbon-carbon double bond. And we have a group here and a group here, which are the same. Is that good or bad? That is actually bad. That means that these two guys are the same, which means you cannot have cis or trans in this case. So it would be neither. And that's because these guys are the same. So as soon as you hit two groups that are the same on the same carbon in the double bond, there's no possibility to make cis or trans isomers. And that's how you know it would be neither in that case on that bottom one. Any questions on that there? Obviously, if we were to name the top guy, we'd probably go somewhere like this: 1, 2, 3, 4, 5, 6, 7 carbons, right? And that would be something like heptene, 3-heptene, 3,4-dimethylheptene would be the name of that. So again, sometimes when people see cis or trans drawn, they just focus in on the two carbons and go, oh, it's only 2 carbons, it's the longest. So you still got to kind of look around the whole thing. Yeah. Any questions on that there? Okay. So let's talk a little bit about reactions that these alkenes undergo. Alkenes undergo what are referred to as addition reactions. And they're pretty straightforward in the sense that this is pretty much what happens. You have a double bond because it's an alkene, and you basically want to add something to it, like A and B. 100% of what happens in these reactions is simply you find where the double bond is, and you need to make room for those things to come in. So the double bond becomes a single bond. So you redraw it with a single bond, and then you put one guy on one carbon and the other guy on the other carbon. And that's exactly what happens in all these reactions, pretty much the same. So in these addition reactions, the reason we need to make room, so for example, if we had this, and I wanted to add, say, hydrogen to it, which is basically two hydrogens, right? Can I just stick another hydrogen on at the end here? I could not, because now that carbon has 5 bonds. So what happens in this situation is this. We're going to isolate the double bond, and we're just going to make it a single bond. So on the other side, everything else stays exactly the same, except that I made my double bond into a single bond. Not one thing changes. And then one carbon gets a hydrogen and the other carbon gets a hydrogen. And you basically just put those on. I'll make them blue. So one hydrogen there, one hydrogen there. You go from an alkene to an alkyne in this case. I'm sorry, an alkene to an alkane. This is what sometimes referred to as the hydrogenation reaction, because you're adding hydrogen. So double bond goes away, makes a single bond, allows for those things to add. This is what is sometimes referred to as a symmetrical addition, because you're adding the same thing. You can't screw it up. You put a hydrogen on one and a hydrogen on the other. You did the same thing here, for example. So let's say we added Cl2, which is 2 chlorines, basically. Yeah. Now, this is a little bit bigger of a molecule here, but the only place that I'm going to be concerned with is, frankly, right here. And the only thing I'm going to change is to make that double bond into a single bond, which means, frankly, you should just start drawing left to right exactly the way it looks, because that's how it's going to end up. So you just copy what's there. So I'm just going to copy what's there. There's an H, there's a C, there's an H, there's an H, there's a C, there's an H, there's an H. I haven't changed a thing. There's a C, there's an H. This is the only thing I'm going to change. This is going to become a single bond instead of a double bond. This will be a carbon, an H, and an H. So I basically just redrew this, changing that into a single bond, and that's pretty much all you need to do. Now what happens is, because they're both chlorine, one chlorine goes to one carbon and one chlorine goes to the other carbon, and that is it. So that is basically what happens in these type of reactions. Double bond becomes a single bond. One goes to one carbon, one goes to the other. These are, again, symmetrical additions, which means you're adding something like H2, Cl2, Br2. One carbon gets one carbon gets the other. They're both the same element. So again, you can't really screw it up. You just put one on each and they both get one. Any questions on that there? Now, we can add something that's unsymmetrical, which means we're actually going to add 2 different things as opposed to 2 of the same things. And those work a little bit different. So let us take a look at that here and see how those work. So let's say we were going to add to this guy here. We're going to add water. When we add water in this case, water is thought of as being H and OH. So that's basically what we think of adding water is H and OH. The same thing's going to happen in this case. We're going to take this double bond and make it into a single bond. So that is this. And again, I'm just going to draw it perfectly identical to each other. And now in this case, instead of adding an H to each, one is going to get the H. So we'll put the H here. And one gets the OH, which would go here. So now we go from an alkene to an alcohol is what this is, because it has the OH group there. Same thing if this was, say, HCl. We would add an H and a Cl. Same thing would happen here. We would draw it exactly the same. Turn our double bond into a single bond. And then one gets an H and one gets a Cl in this case. Doesn't matter if it's like a ring structure like this that has a double bond in it, and you add something like water, which would be HOH. The only part that I'm going to worry about is right there. I'm going to turn my double bond into a single bond. And now one will get the H and one will get the OH in this case. So it works the exact same way. Once again, nothing weird happens. It doesn't break apart into like a straight chain. It's still a ring structure at that point. Any questions on that? So the take home is double bond to single bond, add one to each. Now there is a slight difference that can happen in these type of reactions. When we have, say, something like this, let's do this. Actually, we'll draw that out. All right, let's say we have this and we're going to add water to it, which will be our HOH, right, which is water. Now, the exact same thing happens in this particular case. We're going to focus in on our double bond, and we're going to make it a single bond. Once again, absolutely everything else stays the same. So if I were to draw this, I would start at this end. I'm just going to draw it underneath since I ran out of room over there, and just copy it exactly the way it is. Once again, we're going to turn our double bond into a single bond to make room for what's coming in. But now we have kind of a choice as to, you know, where we can maybe put the H or the OH. We could do two things. We could put the H, for example, here, and the OH here. That's one option, right? Each one gets it. The other option would be to basically do the opposite. And I'll draw that, those guys in red, maybe doing the opposite here. Oops. We'll do that. We could put the H here and the OH here. So this gives us two sort of options as to how we could place these guys because it's unsymmetrical. There actually is a rule as to how you should do it. And the rule is that the hydrogen that's being added should end up on the carbon that had the most hydrogen to start with. So that is the rule. So let's talk about what that rule really means. We basically have two carbons in this double bond that we're looking at, this carbon and this carbon, right? So that is where we made our single bond to add those things in. So directly attached to the carbon on the right is one hydrogen and two hydrogens that are directly attached to the guy on the right. So that guy's got two hydrogens. Now this carbon here on the left has how many hydrogens directly attached to it? There are none directly attached to it, right? Because this is a carbon to carbon connection, right? So there's actually no hydrogens attached to this carbon. The rule says that the hydrogen that's coming in, which would be this guy, should go to the carbon that started with the most hydrogens. In this case, the carbon that started with the most hydrogens is this carbon, which means the hydrogen actually should end up over here like this, and the OH should end up over there. So sometimes you do have an option as to, where to put the H or the OH, and you always want to put the hydrogen on the carbon that started with the most hydrogen. That gives you what is referred to sometimes as the major product. The other one would be referred to as the minor product. And when you draw things, you usually want to draw the major product. So that is the rule. And it happens only when you do these type of reactions where they're unsymmetrical. That means you're adding like water, like HOH, you're adding HCl, you're adding HBr. The H's in all those additions should end up on the carbon that had the most hydrogens to begin with, if there is a difference. So in this case, there was no difference, right? This carbon had two hydrogens. This carbon had two hydrogens, so it does not make a difference. But when there is a difference, the hydrogen coming in should always end up on the one that has the most hydrogens to begin with. And again, if it doesn't make a difference, like in these first examples, you could add it either way. It's all good because it's basically the same molecule if you turn it around. In this case, these are actually two different molecules. This is what is referred to as 1, 2, 3, 4 carbons, which is known as butane. Because this is an OH, it's an alcohol, so it's known as butanol. And this OH group is at carbon number 1. So this is what is known as 1-butanol, which is an alcohol. And that is different than what we drew down here because this is 1, 2, 3, 4 carbons, which is known as butanol because it has the OH group. But the OH group here is at carbon number 2. And this is known as 2-butanol. These are two different alcohols as a result of that difference of where you could add the OH to the H. And the major product should be this guy, where the H gets added to that first one. Any questions on that? By the way, that's how you name alcohols, the same way as you do double bonds or triple bonds. The OH takes the priority. You give the number where the OH is located, and you number to give the OH the smallest set of numbers. So it works the same way. Any questions on that? Hopefully that was your question. Yeah, yes. Yeah, okay. It was cyclopentene with, there's a double bond like this, right? Don't worry, like there maybe, yeah. And it was Cl2. So again, this is one of those symmetrical additions. So you follow the same thing we just talked about. The only part that changes is here, and it's going to become a single bond. So you just would make it a single bond. And then that really frees up a spot here and a here for a chlorine each. Yeah. So that's what would end up happening in that case. So this is a symmetrical one, which we're adding two of the same thing. So it doesn't really matter, obviously, which one you put it on. They both get there. But the key in all these addition reactions is double bond becomes single bond, and each carbon in that double bond gets the thing coming in.